Good morning, ladies and gentlemen. Welcome back. It's already Wednesday before you really had to do anything here. So I didn't want to bother you with having you do anything Monday or Tuesday. I figured just, don't worry about it here for the time being. Hopefully you were able to do other stuff, get caught up. But since we've been gone, we do have to continue where we left off. So that's what we're going to start today. Now, before we get into that point, we are going to just briefly go over what we did on Friday. Now, Friday, we started off the class period by looking through our little spectroscopes or pirate scopes, if you will, and looked at the various tubes of gas to look at their line spectra associated with each gas. And we got some notes, just a few notes here, talking about Niels Bohr and his work with the hydrogen atom, and gave us some really good insights into the hydrogen atom, but his thoughts and hypotheses and ideas could not be taken from hydrogen and moved to other atoms. And so that's where we kind of left off, starting to talk a little bit about quantum energy levels, okay, about how electrons can exist on certain energy levels depending on how much energy they absorb. Well, that brings us to Louis de Broglie, who was one of the early individuals who came up with the quantum mechanical model, okay? If you watch any Marvel or superhero movies lately, you've been hearing about quantum realm, quantum this, quantum that. If a movie doesn't know how to explain something difficult to the audiences, they say quantum, and then it's all good, okay? Yes, that can explain some things, and no, it's not always the correct response. But where the quantum mechanical model kind of came out of was that whole notion about electrons being both a wave and a particle. So a wave being essentially nothing, okay, but really energy, and a particle being something that's tangible, something that is real, something that is to be touched, okay? And so staying with the concept of light, which is what we've been looking at throughout this entire chapter, Louis de Broglie knew that light has both wave as well as particle characteristics. And so what he did was he hypothesized that particles, which included electrons, could also have these wave-like behaviors. So as he continued with this thought, he knew that if an electron would have wave-like motion and is restricted to circular orbits of fixed radius, or radii, then the electron is allowed only in certain possible wavelengths, frequencies, and therefore energy, something we saw way back early in the chapter. So he went ahead and developed an equation that incorporated the wavelength of the particle as well as the mass that moves with a certain velocity. And so he found that if you incorporated not only Planck's constant that we talked about, but also the mass and velocity of a particle, most notably an electron, then we could determine the wavelength here. Now, anytime in physics that, if you take physics later on, it's also something we discussed last semester, anytime you take the mass of an object and multiply it by its velocity, you get what's called momentum. So we're looking at the Planck's constant in conjunction with the momentum. But notice that in this formula, mass is in the denominator position. So that's going to kind of play a role into what we're talking about today. What do you think? When we have a mass with really large mass, what do you think the result of the wavelength would be? So if we had a large mass and we calculated the wavelength, what do you think that would do to the wavelength? Would it make it Smaller or bigger? Who says smaller? Who says bigger? Okay. Now let's talk about that. So if you have a situation, I'm just going to throw up a random calculation, okay? We have two situations here. We have 10 divided by 2 or 10 divided by 10. Which one's going to have the larger result? 10 divided by 2, right? So if this is a calculation, again, I'm just using generic numbers now to simplify it. If we have a really small object in our denominator or a really large object in our denominator, what we can reason is the smaller the mass of an object is, the larger the wavelength we're going to get. And so what Planck was going to eventually say was everything, oh, sorry, not Planck, but de Broglie, what de Broglie was trying to say was everything, including you and I, exhibit a wavelength associated with us. But since our masses are so large that it is imperceivable, the only thing we can do is calculate what our wavelength would be. We can't see it. We can't study it. We can only talk about it mathematically. And there's a video I show in my other class that talks about if we were to take, like the, well, I can't remember it word for word, but essentially what they're saying is if we were to take a wavelength of us, shrink it down to the size of an atom, our wavelength would be the same size as an atom within a solar system. So really, it's really, 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 really small. But we do have a wavelength associated with this. In order to get more understanding of electrons and their movement, since we're kind of building off of de Broglie, because de Broglie talked about mass, location, and velocity of electrons, Heisenberg gave us what's called the uncertainty principle. And really all this means is that fundamentally it is impossible to know precisely both the velocity as well as the position of a particle at the same time. Again, we're mostly talking about electrons. And so what Heisenberg did to justify his statement, his principle, was that he showed it was impossible to take any form of measurement. And every time you took a measurement, you have to disturb it. So the only quantity that can be known is the probability for an electron to occupy certain regions around the nucleus. So even if I take this meter stick and attempt to measure the dimensions of my podium, if I just hold my meter stick above it and try to use my eyes to gauge where the sides meet up, do you think I'm going to get a very accurate measurement? No. But what's nice is it's still here. What's the best way to measure this? Put it right down right there, right? I can line up the edges really nicely, but what did I do in order to do that? What's that? I put it on top of it. Or in the case of Heisenberg, I disturbed it. And so when we try to go and, that's a big object though. Let's say we have to go and try and measure an electron, okay? We have to use, obviously, very different technology to measure an electron's characteristics than this podium. So what we use is we use instruments that use light or a form of radiation. But up to now, we've already been told that radiation is actually energy. and what happens when things with energy interact with other objects. They disturb it. So even when we try to use a light source to measure electrons or other really small particles, we're going to disturb it. We're going to disturb its location or its speed. And so that's why we cannot fundamentally, there's no absolute way for us to have exact knowledge of both velocity as well as position. So it becomes a probability, which is what Erwin Schrödinger went on to describe. So Schrödinger treated electrons as waves in his model. And this is where we have our quantum mechanical model. And so he took extremely high levels of calculus and developed an equation for this quantum mechanical model known as a wave function. And since at the time we could not understand any other element other than hydrogen, this newly found equation was applicable to all the other elements besides hydrogen, I mean, including hydrogen, but also in addition to hydrogen. And so, like before, the model is going to limit an electron's energy to certain values. Again, that's not anything new we've been discussing. But instead of having this notion of electrons going around in a circular motion around the nucleus, using the quantum mechanical model, it does not make an attempt to describe the path that an electron is going to make. So in other words, it could be traveling all over the place. But what it does is it provides a three-dimensional region around the nucleus that we call an atomic orbital. And this atomic orbital is going to describe the electron's probable location. So we've come a long way in our models of the atom. Before we started discussing it, we didn't even know what atoms were. We had to discover what made up an atom. We had to come up with ideas after we discovered what made them up as to how they are oriented. And now we've come to this situation where we have probability calculations of where we think electrons might be based upon electron orientation as well as energy. And actually, when Schrödinger developed all this and all these new ideas about probability and not being able to understand where electrons were actually at, he actually left the field that he was studying this in. He created this incredible equation that allowed us to get a better understanding of how atoms and electrons are working, but he was so essentially philosophically against what this was that he just quit what he was doing and went and studied something else. He's like, I can't even put my head around this right now. So he abandoned what he did, but we kept it. And so these atomic orbitals, again, are going to represent energy levels. We've already discussed the principal quantum number, which we denoted with the lowercase n. And what this does in terms of the quantum mechanical model, it indicates the relative size and energy of atomic orbitals. More specifically, it specifies the atom's major energy levels, which we call these the principal energy levels. And so we number them beginning at 1, with 1 being the lowest principal energy level of an atom, and continuing going outward. And as we proceed through this chapter, we are going to find out that we really only have to concern ourselves with approximately 7 energy levels. And they're going to find out that they all correspond, or at least align to, all the 7 rows of the periodic table. A lot of times you only see 4 up here, maximum of 4, but that's a whole other issue. But as we proceed through this next section of the chapter, we're going to be working with these numbers. So, we have, within these energy levels, we have energy sublevels, which are contained within those principal energy levels. And so, for every energy level, there is an increase of 1 additional sublevel. So in the first energy level, we have 1 sublevel. Energy level 2, we have 2, 3, 4, so on and so forth. And so in energy level 1, where we have n equals 1, we have 1 sublevel, and we call this the S sublevel. When n equals 2, we have 2 sublevels, where we have the sublevels called S and P. In the third principal quantum level, we have 3 sublevels, S, P, and D. And lastly, when n equals 4, we have 4 sublevels, S, P, D, and F. And so what those 4 letters are, S, P, D, and F, we're going to look at those over the next couple of slides. Okay? Because as we build up energy, what those S, P, D, and F labels are what we call orbitals. And really, they're just various energy levels within the main energy level, as well as a 3D orientation. And so I have some changes I want you to make to the slide. Okay. Before I start getting into the notes, I want to make these changes. Okay. See the numbers in the parentheses? I just cross those out. I could not remove them. I don't know how they are permanent on there, but I could not remove them. So we're not even going to concern ourselves with these over here on the left, okay? But I'll talk to you about the changes that I've made when I come to those now. So, as I was mentioning, the atomic orbitals are defined as 3-dimensional regions around the nucleus of an atom that describes an electron's probable location. Now, bullet point number 2, I want you to keep in mind, because before we leave the slide, I'm going to have you jot down some additional numbers. 1 orbital can hold a maximum of 2 electrons. 1 orbital. And so now I'm coming up to some of the things just a few of the things I want you to add. We're going to add some more too. The 4 types of orbitals, we have A as the S orbital. And next to that, I want you to write what I've written. 1 orbital. The next orbital, we have the p orbital, and next to that I have written 3 orbitals. What these statements are that I have put up there are how many orbitals are contained in each of these letters. Bullet point C, we have the d orbital. The d orbital contains 5 orbitals. The s orbital has a shape of spherical. The p orbital is dumbbell, as we see right here. And the d orbitals contain a couple of different orientations. We have 4 that are what are called cloverleaf shaped, and 1 that we call a unique dumbbell. It kind of looks like a little bit of a p orbital with a donut around the waist there. And lastly, the f orbital contains 7 orbitals within it. And depending on who you talk to, oftentimes you'll see books and other references say that the orientation of the 7 f orbitals are too complicated to draw or explain. You might come across some references on the internet that has 3D representations on there, but they may not be confirmed as to those being the shape. Now, the last thing I want you to write on this slide is this. I wanted you to keep in mind this statement, that 1 orbital can hold a maximum of 2 orbitals, okay? Now, you ready to do a quick little mental math? We are going to jot down how many electrons can be held within each orbital. So, starting with the s orbital, we said that within it there is 1 orbital. Anybody tell me how many electrons do you think the s orbital can hold? 2. Bingo. Write down 2, or max 2 electrons for the s orbital. Max 2 electrons. Onto the p orbital. The p orbital contains 3 orbitals. So how many maximum number of electrons do you think the p orbital can hold? 6. 3 times 2. So p orbital is max 6 electrons. You've probably already figured out the d orbitals, if they contain 5 orbitals. Well, 10. So the d orbital has a max of 10 orbitals. Electrons. D orbital has a max of 10 electrons. And finally, F, the big 1-4. 14 is the maximum number of electrons for the f orbital. And I'm having you write those down and us talk about them, because when we get into section 3 is we're going to spend quite a bit of time on section 3. Okay? We're going to chunk it up into 3 separate sections, essentially. Because what we just wrote down about the maximum number of electrons and all that good stuff, that is going to be vital to what we do in section 3. So you're already ahead of the game. Okay? Last slide for the day, folks. So, if you can see on your slides, and I'm not certain you can, but when we look at the p orbitals and the d orbitals, you'll notice that they have little, well, you probably can't really see it, but little subletters underneath them. Like, for instance, this one says px, py, and pz. When we have orbitals that have more than 1 orbital, so p, d, and f, okay, s only has 1 orbital. So p, d, and f, we have these sublevels that we call that are oriented along different axes. We have the x and y and z axes, as well as others, like the z even. We have we have x, y, z, and then we have y, x, y. It just all depends on the 3D orientation. So the 2p orbital contains 3 of these orbitals, 1, 2, 3, which are equivalent in energy. And again, they're just denoted with 2px, 2py, and 2pz. Anytime you see something like that or a question like that where it asks about what does the x or y or z mean, it means the orientation on an axis. So that ends section 2, which means tomorrow we will have a homework check. You will not have a homework check for at least a week after tomorrow. Okay, that's kind of where we're at when it comes to section 3. Now, section 3 is not necessarily difficult. It's just I want to make sure that we have it down pat. Okay, if you can count, you should be okay. So that's where I'm going to leave it at for today. Again, if you need to match up any notes, complete any notes, then I'm going to put this video as well as the video from last week should already be up, so you can go over those